Hello everyone, welcome back to this course. So if you remember, we were talking about determinants in this chapter, which is chapter 6. Okay, I would like to quickly remind you what we talked about last time. So the main definition we had last time was the cofactor expansion along any row or any column. So let me discuss what was the cofactor expansion along the ith row. So given a square matrix n by n, when the question is about the cofactor expansion along the ith row, you just look at the ith row and you look at the entries in the ith row. This is the first one, this is the last one. And then you compute for each entry, you compute the corresponding cofactor. So this one is the cofactor for the first entry, and this one is the cofactor for the last entry. And then you multiply each of these cofactors to the corresponding entry, and then you add them up. Good? That gives you the cofactor expansion along the ith row. And we had a similar discussion for the jth column. And then we computed the cofactor expansion for a 2 by 2 matrix, and we realized that the cofactor expansion along any row or any column, they're all equal to 6. Okay, let's start with a remark. First, we have a remark. Although the cofactor of an entry and also the cofactor expansion along a row or column, they're both numerical values, or they're scalars, but they're different. Just be careful. Okay, very interesting theorem, which says, Theorem 6.1.1, let A be an n by n matrix, then the cofactor expansion along any row or any column, they are equal. Good. So now we're ready to define determinant. Okay, let definition 6.1.5. Let A be an n by n matrix. Then the determinant of A, denoted by det of A, or we use 2 vertical bars, is the cofactor expansion along any row or any column. So we saw in the previous example that they're all equal. That's why it doesn't matter which row you choose or which column you choose. Let's do an example. Well, indeed, let's look at the example 6.1.3. As we computed in the previous example, which is right here on top, the cofactor expansion along any row or any column, they are all equal to 6. That's why the determinant of this matrix is nothing, just 6. Okay, if you remember, we talked about determinant of a 1 by 1 matrix. Now, is there a quick, nice formula for 2 by 2 matrix? The answer is yes. Theorem 6.1.2. The determinant of a square matrix with entries A, B, C, D equals A, D minus B, C. So basically, you multiply the entries in the main diagonal, and then you minus the multiplication of the entries in the off main diagonal or non-main diagonal. So for 2 by 2 matrices from now on, you have a very nice formula. You quickly can figure out the determinant without doing any cofactor expansions. Okay, let's prove this theorem. To prove this theorem, let's do the cofactor expansion along the first row. What if I want to do along the second row? Doesn't matter. What about the first column? Doesn't matter. You're free to choose. Okay, so if you remember, this is just A times C11 plus the entry in that row, the second one, times C12. And if you remember, to compute C11, C12, we had -1 on top I plus j, and we can quickly figure out what are those signs. That's why we have A times +1, and then you rewrite the matrix. However, you're supposed to remove some rows and columns. Here, because of this one right here, we remove the first row, and because of this one, we remove the first column. And then plus B times, and then there's a minus right here. Good, so we put -1, A, B, C, D. Again, we have to remove, because of this one here, the first row, because of 2 here, the second column. Another way to see what to remove is quickly just look at this entry and tell yourself, I have to remove the row containing that entry and the column containing that entry. And you quickly see that this goes here. Good. Okay. Now, let's continue our computation. So this becomes A times determinant of a 1 by 1 matrix D is D minus B times C. Good. So we have a very interesting and easy formula for the determinant of a 2 by 2 matrix. Okay. The next example is about computing the determinant of a 3 by 3 matrix. Okay, let's choose the third row, or we can choose the first column. The question says why. Well, we'll answer that at the end. Let's compute. So be careful, there's a 0 here. That's the reason indeed. So let's compute the cofactor expansion along the third row. So we get, so det of A equals 0 times. Again, let's figure out the sign. So we have plus here, minus here, plus here, minus here, plus here. Good. That's why we have 0 times plus 1 times. Just copy the determinant. And then we have to remove again, as I said, just look at that 0. We have to remove the row that contains 0 and the column that contains 0. Then plus twice minus 1. Remove the row containing 2, the column containing 2. This 2 here, right? This 2. And then plus 5 times plus 1. And then remove the row containing 5, the column containing 5. Okay. You see, since there is a 0 right here, this 0, that will lead to having 0 in the first term. That's why it was a good idea to choose the third row, because there's a 0 here, or the first column. Because when you have a 0 in the entry, then that leads to removing a bit of computation. So the answer is -2 times 2, 3, 1, 2, plus 5 times 2 minus 1, 1, 4. That gives us minus twice. And we have a nice formula we just learned. You multiply the entries in the main diagonal. So 4 minus 3 plus 5 times 8 minus minus 1. That gives us -2 plus 45. So the answer is 43. Great. So we calculated the determinant of a 3 by 3 matrix. Okay, then now let's look at this interesting remark which says the smart choice to pick a row or column is choose the one with many zeros, because then you will have less computation. Okay, great. So I think that's enough for today. Next time we continue by evaluating the determinant of a 4 by 4 matrix. Okay.